I want to talk about Carnot and the cycle. Usually it's times that makes the discoverer, and not the discoverer that makes the times. There are three exceptions I found to this rule. One is Carnot. But if it wasn't for Carnot, no one else would have even looked at the problem. The second is Planck's theory of radiation, and the third is Schrodinger's equation, which we touched upon last time. So Carnot came onto the scene as an engineer. He wasn't interested in understanding or making better the cycle itself. They didn't even know it was a cycle. The steam machine came into existence with what? The mechanism in which it worked was completely unknown at the time, and he was trying to find principles which would guide him to understanding the mechanism of the Carnot cycle, of the cycle itself. Actually, he proposed the cycle. All they knew at the time was that there was an isothermal expansion from a state A to a state B. Afterwards, if they continue the isothermal expansion, they would require heat. So Clement assumed that there would be an adiabatic expansion at the time. And Carnot introduced the fact that you needed an isothermal compression. And in the notes found posthumously after Carnot died, he asked why, in order to develop motive power by heat, a cold body is required. Why motion cannot be produced by consuming heat in the heated body. At the time Carnot looked at the cycle, what was known about heat was through the caloric theory. That is, Carnot believed that any time you had a difference in temperature, you produced work. But caloric theory meant the conservation of work. That is, heat was a substance which, in a certain sense, behaved like radiation. When it was in a dormant phase, it was attached to the molecules themselves. Only when it left the molecules did it appear as heat radiation. So caloric theory mixed energy, entropy, which was to come afterwards, for they're all the same thing, caloric. Now, what could Carnot have used prior to his machine was the fact that the problem of the heat capacities. As far back as Newton, Newton wrote down the velocity of sound as the square root of the pressure divided by the density. Okay? And in 1783, the French Academy started measurements of sound velocity, and they found that it was way above what Newton predicted. Newton predicted an isothermal propagation of sound. That is, sound would be in the condensation and rarefactions of the propagation of sound, that you have enough time for the system to become isothermal. That is, the system would reach its common temperature before it would continue propagating. So this was wrong. They had to find out why. And at this moment, Laplace considered the possibility that it was not isothermal propagation, but adiabatic propagation. That is, the sound passed so rapidly that it didn't have time to come into equilibrium with its surroundings, and it was more isolated, adiabatically isolated type of propagation. So, in this sense, what was known from caloric theory was that there are two types of heat. The sensible type of heat, which you could measure by raising the temperature, which would be the heat capacity an increment of temperature, and the latent heat, which was stored. So caloric theory was at its best when you talked about storage, heat being stored. It couldn't explain things like Rumford's boring of cannons produced by friction, heated up. That was the dynamic part of heat. But it could explain things where there was storage of heat. So heat given up would be like a sponge. You squeeze the sponge, heat would flow out. Let the sponge expand, heat will be soaked back in. So this was what heat consisted of. According to Carnot, you needed the temperature difference. So this was like a difference of water flowing from high to low. Okay? The same amount of water at the top of the hill is found at the bottom of the hill. The only thing is that it's the motion of a fall in heat which produces work, according to him. But he never needed to use the conservation of heat in the cycle. So here I can say that this would be equal to, if I choose now not, sorry, this is V. If I choose not V and T, but V and P, I would have, instead of this, dq in dV at P constant plus dq in dP at V constant. And then I can write this as dq in dt at P constant, dt in dV at P constant, plus dq in dt, V constant, dt in dP at V constant in dP. Okay? This is the definition of the heat capacity at constant pressure. I'll leave T in dV alone, plus dq in dt, which is the heat capacity at constant volume, dt in dP. Why this is important is very little was known about the heat capacities at the time. According to Carnot, this information was done by Laplace before Carnot started his investigation, should have known that it's the ratio of Cp over Cv which is constant. There's an experiment done by Desors and someone else who assumed that the heat capacities were functions of temperature. And Carnot, from this, got the wrong impression that according to him, the heat capacities would be, would increase arithmetically, and the volumes would increase geometrically. That the only function that relates the two of them is the logarithm. So he assumed wrongly that the heat capacity was had this dependence on logarithms of the volume instead of the heat itself, and this produced confusion. But here, clearly, we're going to see that the heat capacity, the ratio of the heat capacities is constant. So, if the system is adiabatic, this is equal to 0. I can solve this dP in dV at Q constant is equal to minus Cp over Cv dt in dV at P constant, Vp in dt at V constant. Okay? Now I can simplify this using Jacobians. This is called gamma minus gamma, the ratio of the two heat capacities. I can write this as T P T V P V P this, change the sign, and this is nothing but gamma dp in dv at t constant. So what you have here is the compressibility under adiabatic conditions, and this is the compressibility under isothermal conditions, and it's increased by a factor of gamma. Okay? So, what Laplace did was to write the speed of sound is v minus dp in dv at q constant equals v square root minus gamma dp in dv at t constant. Okay? 1 over v is rho. So in this case, he increased it by this factor, gamma, Cp over Cv, and came very close to what the academics used to measure in Paris. Okay? So Carnot missed this. Carnot thought that Cp and Cv both vary, but the difference is a constant. Rather, it's the ratio of the two which is constant. And for an ideal gas, it is a true they're both constant. Okay? So this is one piece of information which he missed. Carnot never wrote down this. This cycle in the PV plane. He reasoned from pistons. Okay, there's the piston moving up under isothermal conditions would allow heat to be absorbed at the higher temperature. From B to C, there would be an adiabatic expansion, and from C to D, there would be an isothermal compression. The question is, how do you close the cycle? No one knew. So, one suggestion was, you close the cycle because instead of A, you start the cycle at A prime. And then you close the cycle because the two volumes are equal. Okay? That was Carnot's suggestion. Well, these are isotherms and these are adiabats. And Carnot didn't know either of what these two looked like. So, according to him, you would have equal volumes of the state you started from, the state you arrived at. To Clapeyron, who, after Carnot's death, started to look at the same cycle, and he's the one who wrote down, who designed the cycle in the PV plane, assumed that state D would be reached when the same heat would flow out that flowed in. So his condition to find D was to do the isothermal compression until the same amount of heat flowed out as flowed in. Carnot never used this criterion. Then Carnot said that you do the expansion again to get to the same temperature, but a higher pressure and a smaller volume. And you increase it again to get back to A prime by an isothermal expansion. Okay? This was Carnot's suggestion. Many years after Carnot died, Thomson, who was a postdoc actually, went to work in Paris, and he came across Clapeyron's work of 1834, and he tried to get a hold of Carnot's book, which I think there were about 600 copies printed, and it took him 3 years to find a copy of it. Carnot had to pay for it himself, and he became disillusioned with caloric theory, and he thought his whole theory was wrong. So it took Thomson until 1849 to find a copy of it. Thomson in the meantime, used Clapeyron's suggestion that this cycle should close at D when the same amount of heat flowed out than flowed in. The problem there is that Thomson didn't believe in caloric theory. So why should he use that experiment? Why should he use Clapeyron's suggestion that D should be found in that way? His brother, he spoke it over with his brother James, who was an engineer at Glasgow, and they devised a way of putting to the test caloric theory. Thomson said, "Let me take ice and water, okay, at the same temperature, and then I can, when ice freezes, it expands. Water freezes, it expands, and when it melts, it contracts. So I can do this all at the same temperature, and I can make myself a machine by just repeating the expansion and contraction, and it can do work all at the same temperature." Well, James, his brother, went back into the laboratory and found out, in effect, that water has, as the pressure increases due to the freezing, there's a drop in the freezing point. So work couldn't be done. Plus the fact is that water has maximum density about 2 degrees. And interestingly enough, the LV is positive above and LV positive below. If I work in this area below, I have an expansion here which absorbs heat, but also here there would be an expansion, a contraction, which heat is absorbed. Just the opposite happens. So this seemed like a contradiction, or the production of a perpetual motion machine. I'll come back to this in a minute. So anyhow, the point being is that if we follow Clapeyron, we can start to understand a little about what is going on mathematically. Clapeyron wrote down the same equation for dq in dv, a p constant in dp, plus dq in dp in dp. Okay? Then he said, let me work on an isotherm. PV is equal to a constant. Okay? Let me evaluate this equation, PV constant. So in this case, dP is equal to minus the constant over V squared in dV, which is equal to minus P over V in dV. So I put that in here. I can get out dq is equal to dq in dv at P constant minus P over V dq in dP at V constant times dV. Okay? Now, according to Carnot, the motive power is the area in the graph, P dV, dP in dV, constant. And this, by the ideal gas, is R over V dV. Okay? So I can write the ratio of dP in dV over the heat absorbed, dQ, as RT V dQ in dV P minus P dQ. And according to Carnot, this ratio can only be a function of the temperature. dt, sorry, this is dt, time divided by c. What is c? C is some unknown coefficient of proportionality. This later became known as Carnot's function. And it was Clausius who discovered it, but Joules's suggestion to Thomson that C was the absolute temperature, the temperature itself. So what Clapeyron did was to convert this into a differential equation. And he obtained V dq in dv, P minus P dq in dv, equal to RC. Okay? And there's a method now to solve this equation, developed by Lagrange, where I can look at the characteristics, what they call characteristics, which in this case are isotherms. Okay? So, the isotherms, in this case, well actually, Clapeyron doesn't tell us how he solves it, he just gives us the answer. Q is equal to R, B minus C log P, where B is a constant integration, which can only depend upon T. So to see how he gets this solution, the characteristics of this equation are dV over V, P minus dP over P equals dQ over RC. One solution is A is equal to Q C log V. And the second solution is just PV. We started out with. From Marriott's law, in the English version is Boyle's law, PV is equal to the temperature. And here it's constant. So we have two independent solutions which we combine to get Q is equal to C log V, some function f, which is a function only of V. Okay? And PV we held constant. So here we have Carnot's claim that it's not the heat capacity, which is a logarithmic function of the volume, but the heat. So it's Q, which has an arithmetic progression, V, geometric progression, because you multiply the volumes together. And here you add the volumes. So the confusion to Carnot was that he confused heat capacities with the heat itself. And since he only worked in infinitesimals, that is, he only considered infinitesimal cycles, when you divide through by delta T of 1, it's like the same thing. It's, this confusion is even more enhanced because dt of 1 degree, the difference between Q and C is 1 over the temperature. So this is what led to this confusion. So in this case now, we have these two solutions, and we want to put this back into this equation here. And if we do that, we come out with V Q over V P is equal to R C, or 1 over C dQ in dV P is equal to R over V P over T, which is dP and dt. Okay? So we have here the change in pressure with respect to temperature equals, and this is the ideal gas law we use, but it's more general than that. And this is known as the Clapeyron equation. Actually, it's the Carnot Clapeyron equation. Latent heat, C is still a term which function which was unknown. According to Clapeyron, C was a constant, according to him, but all the data showed that it varied with temperature. Okay? And if I write the total derivative here, it means that P is no longer a function of volume. It depends only on the temperature. And this is for a phase equilibrium, even though we used an ideal equation state. This is due to the fact that the gaseous phase has a much greater volume than the liquid phase. So, for all due intents and purposes, I can use an ideal gas law here, and without causing very much difficulty. So, Clausius puts this into another form. He writes it as R dt over V dq in dV T equals dt over C, which is the ratio of the work done to the heat absorbed. Notice that I have T here and not P. Clausius worked with independent variables V and T, and so this is, and he comes out with this because if this is R dt, V dq in dV at temperature constant is LV, but LV was known to be P because the latent heat was just the pressure itself. This goes back to Holtzman, and in this case, this is dt. The gas law would make this just T. So this is how Clausius obtained the Carnot function. There was a big feud between Thomson and Clausius due to a letter written by Joule to Thomson in December of 1849, suggesting that C was in fact T. And Clausius comes back and says, a letter is not a scientific publication, and I'm the first to have shown this. Or if you don't believe me, it's Holtzman who had discovered it previously in 1848. So anyhow, there was priority disputes going on all over the time. But returning to Carnot, it's not the consumption of caloric that does the work, but it's rather its passage from a hot body to a cold one. Okay? So when you take away caloric theory, you demote the cold reservoir. It's no longer, the cold reservoir was necessary because of the conservation of caloric. What flowed in had to flow out. With the abolishment of caloric theory, work can be converted, heat can be converted into work, and at that point, it's still necessary, but it has been demoted, has a lesser role to play. It's not as in caloric theory. So, there have been many ways of looking at the Carnot cycle. One was to show that caloric theory held at first approximation, and only a second approximation that you could show work being done. So, if you start out with Carnot's principle that the work involved, heat, which I write dq now, times the difference in temperature, times some factor F, which is unknown. Okay? So this was Carnot's principle. that it depended upon the heat, didn't say which heat it was, at the hot or bottom reservoir, the difference in the temperature, and some factor. This is actually 1 over C. Okay? So, Carnot knew the second law, but didn't know the first law. But if we use the first law, that is, I go from A to B. dq is equal to d to c dq plus p, change in pressure and a change in volume, okay? That's the work. Then if I go to the second law, which you did know, I'll write the empirical temperature at this point, which is any monotonic function of the absolute temperature. 1 over 1 minus T minus delta T, V to C, dq. Okay? This would be Abel's expression of the second law. I can multiply through by T. And if delta T is small, I can expand it, and I get 1 plus delta T over T plus in dC, in dq. And then I go back and I compare it with this law, and you see that dP dV is equal to delta T over T times delta Q. So the function, which is 1 over C, in the inverse of the Carnot function, is just the temperature itself. Okay? And this also shows that at first order, I get caloric theory. Second order, I get the work done, the second order effect. So this is just a way of rationalizing its use. Okay, let's see if I want to say something before that.